Okay, good evening everyone. Today we're going to do another integral volume problem. And this one is in James Stewart's Calculus, 5th edition, chapter 6, section 2, number 11. Now, if you'll notice, one thing I've pointed out before and I'll point it out again, is that the rectangle is the single most important part of this, that little infinitesimal rectangle, infinitesimal in the sense that it's infinitesimally thick. So now you always start the rectangle, you always attach one infinitesimal edge of the rectangle to the axis we're rotating around. Now in this problem, our bounds are y equals rad x, y equals x, and that's just this region where the green is. And then we're rotating about y equals 1, which is the dotted black line. Now, here's the deal though. When we rotate this, we're going to unavoidably get some garbage volume that we're going to have to take away. The volume formed by this red stuff in this rectangle here. And observe that the height of the total rectangle is 1 minus x. If you go from the y-axis, the x-axis to y equals 1, that's a height of 1. And then if you go from the x-axis to y equals x, that's a height of x. So 1 minus x is the height of the straight line piece. Now for the curvy nose piece that lies above it, that's y equals radical x, the black curvy piece. Now, 1, 1 is, and 0, 0 are my two sort of endpoints for this region here. This region whose the green rectangle, the region that's containing the green rectangle. Now, to find I rotate if I rotate this whole region around y equals 1, I get something like this, and notice I get a cone, but I have to subtract off the center part of that cone where I've written the word no, because you want to take away the center stuff. So we have to take away the garbage volume. But we just want the outermost stuff, kind of. It's kind of like being in a restaurant and you don't like the stuff in the center of the pie, but you like the outside. Okay, cheesy analogy, but let's get back. Now, here I tried to draw an infinitesimal cylinder in here, and I just couldn't make it work. So what I did, I tried to draw a black piece and cut the red dotted piece out. But let's go down here where we can really read it. So dx is the amplified, really dx is very, very small, but I amplified this guy. So dx is the thickness. Again, the thickness lying along the x-axis, because that's the way we're integrating. And 1 minus, now notice that 1 minus x in black here is the radius of this whole cylinder. And let me run up here. That's the radius of the whole cylinder. So from the bottom to the center. Now, the red, from the top of the little red piece to the center of the red piece is 1 minus rad x. So 1 minus x is greater than 1 minus rad x. Now, the reason why that is because 1 minus x goes further down, and hence it's going to cover, and since we're rotating in the upward direction, it's going to sweep across more room. So, intuitively speaking. So, there's that. Now, so the volume of this guy is the infinitesimal volume dV. Now we want this is called a washer. Now we take the volume of the whole cylinder first, which is this guy, pi times 1 minus x, which is our radius, squared dx, which is the thickness, pi r squared h for a cylinder in geometry. And then minus the inward piece, that's a 1 there, 1 minus rad x squared dx. So that crooked thing is a 1, 1 minus rad x. And now, so we take off we're taking away that center cylinder. Now, so we're going to integrate over arbitrarily infinitely many of these infinitely small washer volumes. So we got volume equals integral dV, which more formally is, I went ahead but we already know what dV is. I went ahead and just sucked pi out of the integral, and we get that. We just integrate. Now, we integrate this whole thing here. Integral dV and is this. Now, as it turns out, the answer, the numerical answer to this, I'm not going to go through all the fundamentals of it. I just want you to know how to set it up. It's pi sixth. You'll get pi sixth when the smoke clears and the air clears, but you just go through basic calculus, and you'll have to go through some annoying algebra, a few annoying steps. But if you can see how to set it up, you're sailing, right? You're in good shape. And something calculus books don't talk about enough, and I want to say a little bit about again, is that if you draw a rectangle where it must have some, where it must lie outside the region, notice that in this problem we had to subtract volumes, right? We had to subtract volumes. I had to subtract the total volume from an inward piece. That always happens when you have a rectangle who has like this red part on the outside. No matter how hard you try, you're going to have to get some garbage area. No matter how hard you try to not have it, and that's why we had to subtract this garbage volume, because that was formed by the garbage area before, and the garbage volume is this red region here. And again, that happens now. That happens when we have a red part on the outside. Now, if there was no red part on the outside, we would have no garbage region. But that's not the case here. So there is some garbage. I hope this helps. And basically, dx, the thickness there forms the thickness of this guy, which I've greatly amplified. I tried in vain to draw it up here, but I drew it much better down here. So there's your dx. And you always integrate. If you go about a horizontal, you integrate with respect to x, and dx is your dx is always in the horizontal direction, and vice versa. Now it's vice versa if you integrate around a vertical. It's always dy. So I hope that helps, and I hope you see what I'm up to. I hope you can see maybe some of the geometry behind it. Thank you.